Hey folks, welcome to your third and final lesson in our unit on waves and sound. In this lesson we're going to be talking about harmonics, which form the basis for all musical instruments and how they produce the tones that they do. So three main goals for this lesson. First, we're going to talk about something called a natural frequency and how it's related to this phenomenon of resonance. Second, we'll revisit the idea of standing waves and how they relate to this idea of harmonics. And then we'll look at how to actually calculate the harmonic frequencies for different types of musical instruments. So starting with this idea of resonance. First of all, it turns out that all objects will naturally oscillate at a particular frequency. It's sort of their preferred frequency of oscillation. This is called their natural frequency. Now, all objects have this. Whether or not we see them oscillating a lot, they have a natural frequency that they will tend to oscillate at. So the question is, what happens if we apply a force at that same frequency? So it's kind of like if we have a swing that's oscillating back and forth, what happens if we push on the swing in time with that natural frequency that it's already oscillating at? Okay. And hopefully what you've seen from your time on the swings as a little child is that if someone pushes you in time with your swinging, you swing higher and higher. We end up with a higher and higher amplitude for our oscillations. This is called resonance. So basically, resonance is just the phenomenon that we amplify a wave if the applied force on that wave or on that object matches the object's natural frequency. Now this can have very interesting results at times. The most classic example is the Tacoma Narrows Bridge situation. Now, what we had here was there was a very violent, strong wind that was hitting this bridge, and it turned out that the frequency of the oscillations due to this wind perfectly matched the natural oscillation, the natural frequency of the bridge material itself. So this is what happens when we get resonance of that type in a bridge.
The bridge suddenly went into a twisting motion. The wind speed was a steady 42 miles per hour. This was enough to keep the bridge oscillating in one of its natural modes of vibration, with a period of 5 seconds.
Yeah, so if we see then the wind's oscillation perfectly matched the natural frequency of the bridge, and that amplified the little tiny vibrations that were already in the bridge until eventually the bridge is noticeably wobbling all over the place, and it did in fact eventually break as a result of the strain of that twisting. So resonance, kind of a big deal. Okay. So now we're going to talk about standing waves and how we can use those to produce harmonics and resonance in different musical instruments. We talked a little bit about standing waves in the first lesson, so just to refresh our memories, we want to review what are standing waves, what produces standing waves, and what nodes and antinodes are. Okay, so if you recall, or if you check your notes, no shame in that, standing waves are this phenomenon where as a wave reflects off of a boundary and then interferes with the oncoming wave coming back at it, so the wave moves along, hits a boundary, and then runs back into the oncoming wave. If we have the exact right wavelength, as it turns out, answer the second question, we can end up with a situation where that reflection and interference causes us to end up having constructive interference in the same place as always and destructive interference in the same place as always, so that it looks like the wave is just oscillating in place. Because if we notice at these locations that I'm pointing to right here, where we get maximum maximum oscillation here, we always have constructive interference. Oh my gosh, why are you doing that? And then there are other locations here where there's always destructive interference that don't move very much at all. The terms for these different locations are, at the place of maximum oscillation, we've got antinodes, and at the places of minimum oscillation, we have what we call nodes. So the nodes don't move very much at all. The antinodes move maximally. here. So again, in order to have this happen, we need to have the exact right wavelength or the exact right frequency so that our waves are always interfering in the exact right way, in the same way at each of these places. And I'm going to bring you back to a simulation that we looked at before where we can send waves along a string. So what I'm going to do is have it oscillate a bit so you can just kind of see what's going on here. Okay, now notice on the right hand side I've got a fixed end, which means that this location right here, the particles are not really allowed to oscillate very much. Okay. Okay, so if I pause that, what you notice is that this fixed end here, we never really oscillate very much. We get these huge oscillations up here, but over at this end right here, there's no movement. If you recall, that means that there is a node always at a fixed end. We don't see big oscillations. It kind of just stays in place. Stop. There we go. Okay. Now, if on the other hand we have a loose open end where the particles are allowed to oscillate freely, then what happens is as it reflects and interferes back and forth, we always end up with an antinode at the end where there's maximum oscillation here. So that's a key idea for us to understand before we head into harmonics, is that if we have a fixed end that we're reflecting off of, then we're always going to have a node at that location. And if we have a loose end, we're always going to have an antinode with maximum displacement. Okay. So when we describe harmonics, what we're talking about are all the different frequencies that will produce standing waves in a particular instrument, either along a string or within the cavity of a pipe, etc., etc. So it turns out there are many different frequencies that will produce this, and all those different frequencies are called harmonics. The lowest frequency, or the longest wavelength that will produce a standing wave in a given medium, is called the fundamental frequency. And then harmonics we can find by multiplying that fundamental frequency by some integer. Okay. Now, how to calculate these depends on what kind of instrument we're talking about. So let's start by considering a string instrument. Now, in a string instrument, what we usually find is that both ends are fixed in place. We don't really have a string like just sort of loose wobbling around. Like it's got, it's stuck in place at both ends. What that means then is that our standing waves have to be such that we have nodes at both ends, so that it's okay that those ending points can't really move up and down. Examples of this type of instrument: anything with a string, guitars, violins, pianos, etc., etc. Okay. Now, to calculate the different, the fundamental frequency and the different harmonics, what we have to do is think of what portions of a wave would fit into that string such that we have nodes on both ends. Okay, so the very lowest frequency, or the very longest wavelength that will allow us to have nodes at both ends, would be such that we can complete exactly half a wave from one end of the string to the other. Okay, so exactly half a wavelength along here. In order then to figure out the frequency of this particular wavelength, our lowest frequency or our longest wavelength that can produce a standing wave with nodes on both ends, we can calculate that by taking the speed of the wave and then dividing it by 2 times the length of our string. Okay. To get the second and third harmonics and so forth, all we have to do is then multiply this wave by 2 or by 3 or whatever. Okay. Next type of instrument to consider is an open pipe. Now, in an open pipe, then, what we find is that both ends are loose. Particles are very able to oscillate back and forth there. So that means that we have to have antinodes at both ends. Example of this, a flute. What we have is an open pipe, nothing closing it off at either end, so we can have maximum oscillation there. Okay. Now, it turns out that the smallest portion of a wave, the longest wavelength that we can fit in there, would again have half a wave fitting into the pipe. Again, shortest distance from antinode to antinode. So to figure out that frequency, again, V over 2 times the length. To get the second harmonic, the second lowest frequency that will produce the standing wave with antinodes at both ends, we just take that fundamental frequency and multiply by 2. Last type of musical instrument for us to talk about is something that's halfway in between the two, where we've got one end that's closed and the other end that is open. So a lot of woodwinds, brass instruments fall into this category because obviously it's closed off where, you know, the person is blowing into the pipe, but then the other end is open. So what that means is at the closed end, we need to have a node, and on the open end, we need to have an antinode. Now, this is probably the trickiest one to consider, because at this point, rather than having half wavelengths fit into our medium, we have quarter wavelengths that fit into our medium here. So we go from the node, the midpoint, over to the antinode, the absolute maximum displacement. And the wavelength of this whole wave then is going to be 4 times the length of this pipe. So we can get the frequency then by taking the speed of the wave and dividing by that wavelength that's 4 times this length. Okay. Now, to get the next harmonic, here's what's kind of funny about these half-open pipes. To get our harmonics, we can only multiply by odd integers. That's a key idea here. For half-open pipes, there are no even harmonics. They're all odd. Because basically what you would find is, so this right here up to this first antinode is the portion of the wave that fit in the first time. If I just multiply that by 2, I don't end up with an antinode at the other end, I end up with a node, and that doesn't meet the requirements of a half-open pipe. So I actually have to go 3 times as far, another full half wavelength, in order to get to my next antinode. And then the next one I would have to go 5 times as far as the first one, and then 7, and so forth. So for a half-open pipe, my harmonics can only be achieved by multiplying the fundamental frequency by odd integers, 3, 5, 7, etc. Okay. Last thing I have to tell you is, obviously you have heard some musical instruments being played in your life. One musical instrument will sound very different from another. So like a violin and a trumpet, both playing middle C, will not sound the same. You won't be able to tell which one is the violin and which one is the trumpet. But that seems weird because middle C represents a single frequency, so it seems like they should all sound the same because they all are playing that same frequency. Now the reason for the different sounds that we hear, different musical instruments, different voices, etc., is that they all have a different, now this I don't know how to pronounce, I've heard it's timbre, I've heard it's timbre, call it whatever you want. But basically what's kind of interesting is that when a musical instrument plays middle C, it's not just playing middle C, it's also actually playing all the other harmonics that go with that instrument. It's not just playing the fundamental frequency, it's also playing the third harmonic and the fifth harmonic, and depending on the instrument, the fourth and the second and all these other things, potentially. Okay. Now, what combination of different harmonics are being played determines the unique sound, the unique flavor of that musical instrument. Okay. Now, the pitch of the overall sound is always determined just by that fundamental frequency, but then that combination of all the other harmonics layered over it give us the unique sound of that instrument. So just to show you kind of what this looks like, if we were to analyze the frequencies being played by a tuning fork, it's only the fundamental frequency. That's it. Which is what causes the tuning fork to sound like a tuning fork. A clarinet, on the other hand, has a good amount of that fundamental frequency, but then we've also got some second harmonic, a lot of third harmonic, little bits of the fourth, fifth, and seventh harmonic also being played. And that combination of harmonics is what gives us that nice, mellow sound of a clarinet playing that same note. Now with a viola, if we look at all the different harmonics being played, fundamental frequency and second harmonic, both with approximately the same intensity. So we're hearing both the fundamental and the second harmonic the same amount. And then little bits of third, fourth, fifth, sixth, ninth, etc., etc. And so that combination of harmonics gives this instrument its unique timbre, whatever. It's what makes it sound like a viola. Right? That is all I have for you folks. Have a wonderful day.